The title of this presentation is Climate-Sensitive Planning and Urban Morphology. One contribution of geoinformation technologies in urban climate mitigation is to provide geospatial information for city planners and practitioners in climate-adapt planning. We will use a case study in Singapore to illustrate how this could be done. One major factor that contributes to the formation of urban heat islands is urban morphology. The heat is stored in impervious surfaces and trapped in street canyons during the night, keeping urban areas hotter than the surrounding natural areas. Geoinformation techniques can reveal the relationship of pattern, trend, form, and structure of urban settlements. It will help to investigate the past and present patterns and trends of urban growth. We have seen this illustration before. The figure shows heat island effect with the temperature decreases significantly in the suburban area. The concentration of tall buildings, infrastructure, and transportation in high-density urban areas increases heat absorption and emission, mainly from materials like concrete and asphalt. This effect has been illustrated in Practicals 1 and 2, where we analyze the relationship between land surface temperature and local climate zone classification. Temperatures from natural land covers and low-rise developments are lower in comparison with high-rise central districts. Urban heat islands occur when the temperature in the urban environments is higher than the surrounding areas. High surface temperatures lead to elevated air temperatures, especially at night. They also cause greater air conditioner use, which increases energy costs and air pollution. However, we can create climate-adapt planning to increase green space, more trees to provide shades, and improved urban morphology for better air circulation. Additionally, the type of roof we choose may have a big impact on the energy efficiency, durability, and even the total environmental imprint of our homes. New climate-adapted building materials can be used to mitigate extreme high heat storage. Ultimately, urban heat islands also increase heat-related discomfort, illness, and death. It has a disproportionate impact on disadvantaged communities, and we will address this issue in the next topic. In Zhang and Yun's 2023 paper, entitled Multi-Climate Sensitive Planning Framework to Mitigate Urban Heat Island Effects, a case study in Singapore. They represent a framework of urban planning practice that incorporates geospatial and meteorological data in 3 steps. First, the identification of hotspots in urban heat island. Second, conduct wind assessment and mitigation options. Third, future design proposal with implications based on previous conclusion. This figure shows the workflow of the 3 steps. The input used for hotspot identification is a high-resolution digital elevation model and the calculation of sky view factor, which we have introduced and included in the practical of urban multi-scale environmental predictor. Local weather stations with historic records will provide the air temperature input. For the second step, wind potential evaluation, input required are again a digital elevation model and wind frequency data. Then a frontal area density is calculated. Finally, with the urban permeability map, a wind potential evaluation map is obtained. Before the third step, urban design implementation, there is a step 2.2, spatial implication, where the hotspots are studied separately with a proposal of wind path. More details in the next slides. The proposals will be used as an input for the last of the implementation. In this slide, we look at more details of the processing steps. For step 1, the sky view factor is defined as the ratio of the amount of sky seen from a given point on a surface to that potentially available. It is an index that describes urban canyon geometry, which plays an important role in regulating long-wave radiation losses. The detail of parameters and equations are referred to the paper. Previous studies show that urban heat island intensity is closely related to sky view factor, and one report indicated that increasing sky view factor by 10% will decrease nocturnal urban heat island by 0.3%. The equation of sky view factor and air temperature increment are printed in the top right-hand corner for quick reference. The urban-rural air temperature difference in degrees Celsius were collected and analyzed with data from surrounding meteorological stations. After the identification of hotspots, in Step 2, they calculate potential wind path and a permeability map to arrive to a distinct scale assessment. Urban pedestrian level wind as a mitigation potential for urban heat island was assessed through urban permeability map. For urban scale morphological models, urban permeability is often applied to assess surface roughness. The building surface area facing the incoming wind direction at certain height is calculated. Potential and existing air paths were identified based on urban permeability map and prevailing wind directions. The figure of frontal area density at the lower right describes the equation and the wind frequency data. That is the probability of wind based on experience. It is added with height distribution to provide spatial implication. The figure to the left is the hotspots, or the urban heat island map at 2 by 2 kilometers. To the right, the figure shows annual wind probabilities calculated from wind frequency data of 18 weather stations. This figure shows the wind path detection of East Singapore with local wind rows of the same monsoon season. First is the northeast monsoon season from December to March. Second is the south monsoon season from June to September. The resolution of the map is 200 by 200 meters. After Step 1 and Step 2.1, the outputs are used to facilitate urban design. It aims to show, first, how to apply the design-oriented microclimate analysis into the planning practice, and second, develop heat-reducing and cooling, improving urban morphological prototype and guidelines. This is a case study in Singapore. As shown in the figure on the bottom left, to create wind path to elevate urban heat island effects, we can install an arterial road, or create a green corridor, or to develop only low-rise built areas, and lastly, by varying building heights. In the figure for Step 3, Evidence-Based Urban Design, it shows an integrated design with a buffer green zone in the middle, a low-rise development, and an arterial road. To illustrate how general climate-sensitive strategies are suggested for neighborhoods with different densities, land uses, and locations, a selected district in Singapore is taken as an example. The figure on top left shows the reserved wind path among built-up area and open or green spaces. The figure on the bottom left shows the different development densities of the built-up areas. 4 representative scenarios at the neighborhood scale are defined based on the density, land use, location, and climate assessment. The suggested prototype with mitigation strategies in 4 scenarios were designed at 250 by 250 meters site. The figure to the right is a land use map and location of the 4 scenarios. Scenario A, industrial, low density, located at the gateway. Scenario B, commercial, high density, located along air paths. Scenario C, residential, low density, located at buffer zones. Scenario D, mixed use, medium density, located at inner streets. This figure shows the 3D impression of the climate-sensitive prototype of building morphology in 4 scenarios. The scenarios are created with the recommended parameter settings for GPR or gross plot ratio, and lambda p, the site coverage ratio. In each scenario, 5 indicators are described, including the control over 1. The site coverage ratio. 2. Vary building height. 3. Greenery between blocks. 4. Design porosity of greenery, integrated in higher levels. 5. Wind path for secondary wind. In this talk, we use a research paper of Zhang and Yun to illustrate how geoinformation technologies can be applied in climate-sensitive urban design. First, a GIS-based platform is used to integrate meteorological and morphology data. The platform allows manipulation of inputs from multi-spatial scales for urban design purposes. Different scenarios of planning complex, such as site structure, density distribution, and land use pattern, can be proposed for climate-adapt solutions. Here is the reference of Zhang and Yun's paper. And we also provide a link to a YouTube channel of Hans van der Kwaas. In his channel, there are many examples of using GIS for urban climate adaptation in planning. Please check them out.